I started yesterday, chemistry 156, physical chemistry 1. And that is my name. And today I'm going to discuss Unit 2. The topic is concentration, the rate law, and experimental determination of rate expression. Yesterday, I did explain to you what you understand by the rate of reaction, and that is the time rate of change of concentration, the factors that affect the rate of reaction, and the mechanism of a reaction. So today we're going to take one of the factors. I did say that concentration, just a minute. Okay, sorry. We are back again. Can you hear me? We are back again. And today I'm picking one of the factors, and that is concentration. Others are temperature, the nature of the reactant, and the presence of a catalyst. So the purpose of carrying out the experiment to determine the rate of reaction essentially is to determine the rate law. Once you know the rate law or rate expression or rate equation, then you can actually predict, explain how fast a reaction is going. So the objective of this unit 2, is you will learn how to write the rate law. When I say the rate law, essentially the same thing as the rate equation or rate expression. I have used 3 phrases now. The rate law, the rate equation, and the rate expression, they mean the same thing, okay? And how you can use it to predict the speed of a reaction or velocity of a reaction or the rate of a reaction. And then how do you determine the experimental rate law? So when you are carrying out an experiment to determine the rate of a reaction, what you should try to bring out is the rate law. And once you know the rate law, then you can explain how the speed is, because it relates the rate of the reaction to the concentration of the reactant. And you'll be able to explain the rate of the reaction. And expected outcome at the end of this unit, you'll be able to know the effect of concentration, how concentration does affect the rate of a reaction. And now you can determine the order of the reaction. And then you can write the rate law or rate expression. And now again, more importantly, you can do some calculations. So you are expected. So as we go along, these are the things you should be able to know and gain from this particular unit. Okay, so this is the rate of a reaction is a function of factors such as concentration, temperature, catalyst, and the nature of the reactant. But right now, we are picking concentration. So let us consider one of the factors, and that is concentration. Look at concentration and the rate law. I told you that the purpose of this particular unit is to determine the rate law. Once you know the rate law, then you can say a lot about the speed of the reaction. So the rate of most reactions change when the concentration of the reactants change. And that is true. As you increase the concentration, you are increasing the number of particles, and you are increasing the molecules, number of molecules. So they have so many of them. They are very close to each other. They react, and the result you are going to get is more of the product. So this is how concentration can affect the rate of reaction. That is discussing it like that, but can you bring out an equation that will help you to explain it very well? And that is why you have to determine what you call the rate law. So chemical reactions are usually very fast, or they produce more when you increase the concentration. It depends. Sometimes if you put a poison in the system, it can reduce the rate of a reaction. So as you can see, In general, the rate is proportional to the concentration of the reactant raised to the appropriate powers. Those powers we are talking about, they are like indices, they are like exponents. If you've done indices in mathematics before, you will understand very easily what you mean by exponents and power. So the rate of a reaction is proportional to the concentration of the reactant. I'm emphasizing the reactant, not the product. It's proportional to the concentration of the reactant. It's like, very trivial example, you spend money according to what you have in your pocket. You have more, the tendency is there to spend more. So the rate of a reaction is proportional to the concentration of the reactant raised to the appropriate powers. Those powers are what you call the indices or what you call the exponent. Look at that. Consider a reaction. Look at the reaction there. A reacting with B. The X and the Y, they are stoichiometric factors. For example, 6 is undefined reaction, but look at the one below, hydrogen reacting with oxygen, and that will give you H2O. So equation 6 is like what you have, like hydrogen plus oxygen to give you water. The reactants are A and B. Remember I taught you yesterday, this is undefined reaction. It's undefined, but the one below, hydrogen plus oxygen to give you water, that is a defined reaction. Look at what I'm saying. In equation 6, look at equation 6 there. The reactants are A and B. And then I said equation 6, the molar coefficient, or what you call the stoichiometric factors, the mole ratios, they are there. So you can write a general rate law, rate expression, rate equation. I'm saying the same thing. Rate law, rate equation, rate expression, they are the same thing. I taught you yesterday, the reactants are A and B in this case. If you want to write for the decrease of A, you write equation 7A, the A over the T. Remember that bracket covering that A is a molar quantity. It's like mole per dm³. And then I told you if you have a stoichiometric factor, a coefficient, you divide it. Look at 1 over X. And that will be equal. Because if you remove the K, essentially what you put there is the proportionality constant. So everything on your left stands for rate. And A is a reactant. That is why you have negative sign in front of that 1 over X into the A dt. And that will be equal to K into A raised to power N. That N is what we call the exponent, or what we call the power of A. Then is the product of that, B raised to power M. That M is the order, is the power, is the exponent of B. So that N and M, they are powers with respect to each of the reactants, A and B. Okay, you can take the second one, B is also a reactant. Okay, then because it's a reactant, you put a negative sign in front of it. And then you can write the A over the T. You can use any of them, 7A or 7B, to represent the rate of a reaction. If I remove that equality sign, I want highlighter. Yes. Okay. If you remove the equality sign, you can write like this. I told you the whole of this, I've circled it. That one stands for rate, so I can write R, capital R. You see there? Capital R stands for rate, and that is, instead of putting equality sign, I can put proportionality sign like this, and that will be equal to A, the reactant A, raised to the power N into reactant B raised to the power M. If I remove this proportionality constant, I can put K there, and I put equality sign. So instead of using 7A, I can use 7B. But everything on my left-hand side that I've just circled stands for rate, including the negative sign. Okay. So I've removed it now. So I'm going to another. Okay, you have equation 7. K stands for the specific reaction rate or specific rate constant. The exponent N and M are called reaction orders. And the sum of the M plus N is the overall order of the reaction. Look at that. N is the order to, get this very clearly. N is the order with respect to A. M is the order with respect to B. And the overall order of the reaction is the sum of N plus M. Remember, N is with respect to A and B with respect, M is with respect to B. So if they ask you what is the overall order of the reaction, then you say it's N plus M. And that equation 7A or 7B is what we call rate expression, rate equation, or rate law. The rate law is the experimental relationship between the rate of the reaction and the concentration of the reactant raised to the appropriate power. And that is a very short way of describing the rate law. In fact, it summarizes what goes on in a reaction. That at the beginning of a reaction, the molecules are very many, they are reacting very fast, they collide, they form a lot of product. But with time, the reaction will just be decreasing because the number of molecules are also decreasing. And so the rate law is a short form. It's just a short way of describing what is going on in that particular reaction. Okay, if you look at this, I have told you in equation 7, the sum of M plus N is what we call the overall order of the reaction. And equation 7A or 7B is what we call the rate equation, rate expression, or the rate law. Look at that. The rate law is the expression for the rate as a function of concentration at a fixed temperature. So anytime you are doing an experiment, you need to use a thermostat to keep the temperature constant. If the temperature changes, it means you are looking at two variables, concentration and temperature. And that is why you need a thermostat to maintain the temperature constant or relatively constant. And then if you do that, you have to determine the rate law. So how do you actually determine the rate law? That rate law has to be determined experimentally, has to be determined, mark what I'm saying, determine experimentally. If you are not going to determine it experimentally, when we get there, I will tell you what you should look for. So what do you do? Well, we're going to determine that rate law, equation 7A or 7B. How do you determine the rate law? You want to know the effect of each of the reactants. For example, on defined reaction, A reacting with B. What is the effect of A on the formation of the product? What is the effect of B on the formation of the product? So you need to monitor each of the reactants. It's like you want to fight 3 people at a time. This is a trivial example. It is wise to face one at a time. After that, you face the second one. For you to face 3 people at a time, it's a little bit difficult for you. And so experimentally, all the reactants, we keep all of them constant. If there are 2, we keep one constant and monitor one of them. When we are done with that, we move to the one we kept constant, change the concentration, while the first one will be kept constant. And so you deal with one, if there are 3 reactants, you keep 2 constant and monitor the changes, the reaction of one of them. When you are done with the first one, you keep the first one, the last one constant, and then you monitor the variation of the second one, how it changes with time. It's the same thing. So whether there are 6 reactants, you keep all of them except one and monitor the changes. Essentially what you get is concentration with time. For example, if I give you, or mommy gives you 100 naira, in the morning, times 0. When you spend 20 naira, where after 2 hours, what you have is 80 naira after 2 hours. If you spend 20 naira again, what you have is 60 naira after maybe 4 hours. So you have readings like that. You can find out whichever reactant is decomposing with time. So what you have in your hands are concentration and time. You can plot a graph. And when you find the slope of the graph, at time is equal to 0 at initial time, and that will give you the rate of a particular reaction, which later I will refer to as the initial rate. Look at that. Experimental determination of the rate laws. I told you it has to be determined experimentally. Why is it so? It is because you want to find out the effect of each of the reactant on the rate of formation of the product. And so because, again, it is because each reactant will react the same way. So it's going to affect the reaction in a different way. And these are some of the reasons why you need to determine the rate law experimentally to find out the effect of concentration on the rate of reaction. Okay, so how do you determine equation 7? I told you that equation 7, whether 7A or 7B, has to be determined experimentally. So what do? You can see from the slide before you, it is necessary, very necessary, to study the mechanism which changes the concentration of each of the reactants after the initial rate of the reaction. And so we're going to find out a particular reaction. Take a hypothetical reaction. A reacting with B. This is a defined reaction. I hope I started teaching you yesterday, defined and undefined reaction. A and B are the reactants. The product something. So it's like A is nitrogen, B is hydrogen. And the product, obviously, is going to be ammonia. But in this case, I did not find the reaction. So it's undefined. So let us study this reaction. We want to find out the rates of this reaction. And then after that one, we're going to find out the effect of each of the reactant. A, how does it affect the formation of product? B, how does it affect the formation of product? Then later we'll write the rate law. And then from the rate law, you will see clearly the effect of concentration on the rate of reaction using what we call the initial rate method. So why am I using the initial rate method? It is because at the beginning, reactions are very active. But with time, all the molecules will be decreasing because they have been, all along, they are consumed to form product. And so the rate of the reaction will be decreasing. And that is why initial rate of reaction is very important. And so you find the slope when you plot your graph, when time is equal to 0. Whether it is a curve or a linear plot, you find the rate at time is equal to 0. As the reaction proceeds, I've already explained that as the reaction proceeds, the concentration of the reactant decrease, and it may be difficult to measure the change accurately. So that is why initial rate of reaction is very important. As time goes on, you will be hearing initial rate of reaction. That is, you find the slope at time is equal to 0. That will give you the initial rate of the reaction. Look at that. I want to find the rate law for that reaction you just seen, A reacting with B. So what do? I will prepare a standard solution of A and B with initial concentration. You see that A with a square and a subscript 0. That 0 stands, anytime you see something like that, it stands for the initial concentration. You also see B and the subscript is 0. It also stands for initial concentration. That bracket surrounding A or B, the bracket, it stands for mole per dm cube. So the temperature of the mixture should be fixed. Why should it be fixed? It is because if you don't keep the temperature constant, it means you are studying 2 variables at the same time. And that is difficult for you to actually interpret. So let's go on. How do we do this? You take a known concentration of A, and you take a known concentration of B, and you mix them. And then with time, it depends on the reaction you are doing. Maybe after 1 hour, you find out what is the amount of A that is left. Let's take A to be 100. and take B to be 50. So you put them together. Remember, 100, whatever, I'm talking about mole per dm cube. It's like a standard solution, and I'm taking a no volume. And the concentration is like 100 mole per dm cube. So A is reacting with B to give you product. So with time, A is decreasing, B is also decreasing. And so I will monitor A. And then what I have, the information I have about A is concentration that is left with time. If you like, you can monitor the concentration that is formed with time. But it's good. If you know what has disappeared, you will know what is remaining. So you just find out whatever is remaining. So with time, after, let's say, like 2 hours, you can stop it. And then you find out what is the quantity of A that is left. You started with 100, it's decreasing. Now it is 90 after 2 hours. You carry on with the experiment. You have a way of finding out. You can titrate. You can use spectroscopic means to find out the concentration of A that is left. Then after about 4 hours, you find out you can titrate. You stop the reaction, or you slow it down, or you freeze it. And then you find out what is the amount of A that is left. Maybe 40 has left, 60 is remaining. That means after 4 hours, 60. Maybe after 6 hours, 40. After 8 hours, 20. And so what you now plot a graph. That is the type of graph I gave to you yesterday. Linear graph and non-linear graph. So it can come out as linear graph or non-linear graph. And then you can find your slope at time is equal to 0. If it is a curve, you can extrapolate, you put a target and you find the slope of that particular curve. At time is equal to 0. That will give you, because you are plotting concentration against time. So it gives you concentration over time, that is rate. And then if you determine that slope at time is equal to 0, that becomes your initial rate. And very important, that is the slope with the value that we are very much interested in with. So you can stop, and then you can move again. And instead of using 100 of A, you can decide to go to 200 of A. You keep B constant. And then you monitor it again. What is the amount of A that is left at time equal to this? What is the amount of A? You just titrate, or you find out there's a way, it depends on the experiment, to find out what is left of A at any time. I've changed it to 200 now. I can find my slope, plot my graph, similar to the first one when it was 100. I can find my rate. I can decide to go to 300, but I keep B constant. I told you don't disturb B, just monitor one of them. When I'm through, I can now compare. When it was 100 mole per dm cube, when I performed the experiment, keeping B constant, what was my rate? I will get it from my graph. I will go to the graph when I change the concentration to 200 mole per dm cube. I plot my graph with time, concentration with time. What is my rate? And then I changed it when it was 300 again. The similar graph, what is my rate? When it was 100, I know my rate. When it was 200, I know it. When it is 300, I know it. If they remain constant, that means the order with respect to A is 0. If I double the concentration and the rate now becomes double, it means the order with respect to A is 1. If I double my concentration from 100 to 200 and the rate increased 4 times, it means the order with respect to A is 2. So this is a very simple way you can find the order with respect to each reactor. When you are done with A, you go back. You keep A constant. Let's say for 100. B was 50 before. You can now monitor B at 50 moles per dm reacting with A. You plot a similar graph. And then you can double the concentration of B to 100. You monitor it, you plot a similar graph. You can't increase it to 4 times. You monitor it, you plot a similar graph. When B was changed from 50 to 100, if the rate of the reaction remains the same, the order with respect to B is 0. When B was changed, was double, if the concentration was double, if the rate was also double, the order with respect to B is 2. When you increase the concentration of B 4 times, quadruple. If the rate, when you increase the concentration of B 4 times, okay? When you increase the concentration of B and you find out that you double it and the rate now increase, 4 times, it means the order with respect to B is 2. Obviously, it's here. So I've determined the orders with respect, don't be confused. I determined the order with respect to A. Is it 0? If I double the concentration, what happens to the rate? Is it double? That is 1. If I double the concentration, the rate remains the same, is 0. If I double the concentration, the rate is also double, is 1. If I double the concentration, the rate increase 4 times, the order is 2. That's exactly what I'm telling you. And so you can just, immediately you see the values and see the concentration, you can know the rate with respect to each of the reactants. So you've determined the order with respect to A, determine the order with respect to B. So essentially, what is left is to write the rate law. Then you go and write the rate law. Okay. As you can see on the slide there, if the rate quadruples, increase 4 times, when the initial concentration of A is double, then the order with respect to A is 2. If the rate of reaction doubles, when the initial concentration of A is double, the order with respect to A is 1. Then you can see from the screen, if there is no change in the rate, the order with respect to A is 0. That is when you double you increase the concentration of the reactant, the rate is not changing. And then it means with that particular reactant, it's a spectator. It's not actually affecting the rate of formation of the product. So with those values, you can write the rate law. So let's see how you can write the rate law now. That is example. For example, consider the reaction. A reacting with B to give C. The rate, the experimental rate law for the above reaction, I told you rate is equal to K. Equal to K raised to power, the power to the, there's a power there of A, and B raised to power 0. From that example, you can see there, the order with respect to B is 0. Anything raised to power 0 is 1. So you can even leave the equation. The order with respect to A is 1. You have 1 there. If it is 0, we put it. If it is 1, we don't write it. Everybody will assume that it is 1, including you that is listening to me now. If it is 2, we put it. So essentially what you see then, rate is equal to K into A raised to power 1. There is 1 there, B raised to power 0. So that particular expression, that is what you call the rate law. And if they ask you to write out what is the overall order of the reaction, it's 1 plus 0, which is equal to 1. If they ask you what is the order with respect to A, it's 1. What is the order with respect to B? Is 0. What is the overall order of the reaction? It's 1 plus 0, which is 1. So this is how you can write the rate law. Remember, I said the experimental rate law for the above reaction is I have determined this particular order by carrying out experiment, by plotting graphs. And from the graph, I was able to know the initial rate. And I compared the initial rates. At initial concentration, double the concentration, increase the concentration maybe 4 times. That will give you an idea how to find out what is the rate of reaction. As we go on, look at that. I said the overall order of that reaction I've just considered is 1 plus 0. This is a very good example. Take a hypothetical reaction. B and C, they react to form a product D. The following data were obtained from 3 experiments. Look at B plus C. B and C are the reactants, and D is the product. So how does B affect the formation of D? How does C affect the formation of D? You need to perform experiment to find out how they do it. It's at the end of that you can find the order with respect to B. You find the order with respect to C, and then you can write the rate law. Remember, the rate law will involve the reactant. I told you rate is equal to K into B raised to something. What is that something? You don't know. You have to determine it experimentally. And C raised to power something. It could be M. What is M? You don't know. You have to perform an experiment to determine that order. So look at your left-hand side of that table. Experiment. Experiment 1. I took 0.15 molar of B. Remember, look at the top. I bracket the B. That bracket stands for mole per dm cube. Look at C. I took 0.075 molar. Look at B. I took 0.15 molar. Experiment 1. Look along that line. Then I determine the rate of formation of D. Okay? By plotting a graph, I monitor what is the concentration and order. I plotted the graph, and I was able to get that rate. And that is 3.5 times 10 raised to minus 3 mole per dm cube per minute. It could be per second, it could be per minute, it could be per week. It depends on what you are talking about. But most of our calculation, you'll be working per second. So I moved to experiment. Let me go to experiment 3. Please follow it. Go to experiment 3. From 1 to 3, when I got to 3, I kept B constant. I took the same thing, 0.15 molar. Then I went to C. It is C I am monitoring now. And I moved from 0.75 to experiment 3, 0.15 molar. I have doubled C, but I kept B constant. Remember, I'm using experiment 1 and experiment 3. I'm going to compare them now. I found I kept B constant, and I changed the concentration of C. Look at the rate of formation of D. It has doubled. 3.5 times 10 raised to minus 3 times 2. You move up to 7 point. That means this C is actually affecting the concentration of the rate of formation of D. And then I'm done with C. Those values, experiment 1, the data I have there, and 3 will help me to find the order with respect to C. Let me go to B now. In B, you take experiment 2 and experiment 3. Why are you taking 2 and 3? Look at, I have kept C constant. C is 0.15. Experiment 3, C is 0.15. But look at 2 and 3. You can go up. If I'm leaving 3, 0.15, and going to 0.3, I have double that. And then I move for 0.15 to 0.15. I kept C constant. When I do that, look at the rate. Go to your right-hand side, rate of formation of D. What happened? When I double from 3 to 2 of B, I double also the rate. So, oh yeah, what will you say now? I said if you double the concentration, take 1 and 3. I double the concentration of C. I kept B constant. And the rate is now double. What is the order with respect to C? From what I've just taught you now, is 1. Oh yeah, take the other one, 2 and 3. When you move from 3 to 2, and I double B, and look at my rate, you move from 7.0 times 10 to minus 3 to 1.4 times 10 to minus 2. What is that? Is it double? If it is double, it means the order with respect to B is 1. Then go and write the rate law. You move ahead and write the rate law. How will the rate law be now? In a minute. Can you give me the highlighter? Highlighter? No. Look at that. I've determined the order with respect to B and C from the values. So I can write rate. Look at the way I'm writing. Look at your screen. The arrow stands for rate. The K is the specific rate constant. And I'll write B. We've determined the order with respect to B, and it is 1. You don't need to put 1 there. Don't put 1 there. We assume everybody that can read this kind of experiment knows that it is 1. Then you also determine that C is also 1. And that is the rate law. What is the order with respect to B? 1. What is the order with respect to C? 1. What is the overall order of the reaction? 1 plus 1, and that is 2. So that is how to That is how to determine the order with respect to each of the reactants. What is it? Okay, this is another experiment, very quickly, before we close. Okay, I am looking at the oxidation of bromide by bromate. You can see it from the senior secondary school. You must have been introduced to what we call ionic equations. So you have like potassium bromate, and I don't need to deal with the potassium or sodium bromate or the sodium. I take the part of it that is effective. So this is ionic equation. And you have bromate, and is oxidized by bromide. It could be potassium bromide. The K is away. The K and the sodium and the aspartators. These are the effective part. If you do it in acidic medium, that is sulfuric acid there. I'm not interested in the sulfate, but the proton aspect of it. And if you perform this reaction, you find that you have bromine water and H2O. There is an arrow somewhere here that is not indicated. There's an arrow here. Okay, so it will give you bromine water and H2O. Of course, the bromate and the bromide and the sulfuric acid, they are all like transparent. They are like 7-Up. But immediately the bromine water start coming, you know the color of bromine water, and then you know that the reaction is taking place. Look at the experiment I did. On your left-hand side, you have experiment 1, experiment 2, experiment 3, experiment 4. Look at the concentration. You have 0.05 of, so I'm dealing with three reactants. I'm going to keep 2 constant and vary one of them and find out how you can form bromine, okay? Relative initial rate of formation of bromine. Or formation of bromine. Look at experiment 1. I took 0.05 molar of a known volume, okay? I added to 0.25, added to 0.30. I did the experiment, plotted my graph, find my rate, okay? I just remember relative initial rate of formation. This is like 1 times 10 raised to minus 3 mole per dm³ per second. I have divided by a particular value to remove all the fractions from there. That is why it is relative initial rate of formation. Then I moved to experiment 2. Look at how I kept the first one. The bromate constant, 0.05. Look at how I kept the bromide constant, 0.25. Look at how I doubled the concentration of the acid, 0.60. And immediately I did that, it changes to 4. The rate of formation has increased to 4. And I told you, when the thing increases, if you double the concentration and the rate, or the relative rate increase 4 times, quadruple, it means the order with respect to the proton or the acid is 2. And then let's take another one. So I've determined for that of hydrogen now. Let's take another one, whether it is bromate or bromide. I'm going to take, let me take 2 and 3 and see what happens. Take 2 and 3. I am keeping 2 constant and vary one of them. If you take 2 and 3, you see for the bromate, you see 0.05, 0.10. Then I went to the bromide, 0.25, 0. So I kept it constant. I went to the acid, 0.60, 0.60. And I found that it changes from 4 to 8. What is that? It's double. When it doubles, when the rate of formation of that bromine water doubles, and then essentially, it means the order with respect to bromate is 2. If it doubles, it's what? It is 1. If it increases 4 times, it is 2. If it doubles, it is 1. If it remains the same, it is 0. So this is how you can get a table like this from the data you have here to calculate the order to respect to each of the reactors. But look at 4. I have I decided to put some, you can suspect, put values there, and then find out how you can calculate the order with respect to bromate. Okay, so I have not found out the order with respect to bromate. Maybe I will give that to you as a quiz or a test. Oh yeah, let's go now and write the rate law. for the 3 reactants. Look at below. Rate is equal to K. One of the reactants is bromate raised to power L, then followed by bromide raised to power M, followed by the proton, the acid raised to power N. What is N? What is M? What is L? So you need to find out from that table. I have done 2. I find the value for N for you. 1 to 4. When it increases 4 times, that is 2. I have found the first L for you. When you move from 4 to 8, it doubles. That is 1. So what is the M? Can you determine the M? You cannot right now. But if I fill that column for you, or what do you call it, 4, if I fill it for you with some hypothetical figures, then you will be able to calculate what is M. So this is how to determine. Look at the process of calculation. Okay. Look at what I did. I want to tell you how I calculated. I was able to get N. I took the first layer like that. K is equal to 0.05 raised to power L. The value from that table, I put it there. And then I took the second rate, which is 4, and K is there. And I took all the concentration along that road. I put them there. So what we look at is K. K is constant because you keep the temperature constant. So K up, and the lower part, numerator and denominator, they will go away. So those K will go away. Look at this, they are the same. They go away. Look at this, they are the same. They go away. So this is the only thing you can deal with now. So bring it out. If your mass is good, you still have 1 to 4. 1 to 4 on your left-hand side. 1 to 4 in mathematics is 1/2 raised to power 2. And then look at what is left. 0.30 raised to power n, 0.60 raised to power n. 0.30 times 2 raised to power n is the same thing. So if you want to change the numerator to what the denominator will be, if you want to remove it, it means twice the numerator is equal to the denominator. And if you do that, because if you take the top, say 2 times 0.30 raised to power n, it will give you what is below. So you're left with 1/2 raised to power 2 equal to 1/2 raised to power n. Mathematically, what is the value of n? And that is equal to 2. That is how I got that. So you need some okay. Now, having done that, the exponent in the rate law appears to be unrelated with the rate equation. If you go to equation 7, the molar coefficient is not the same thing as the rate, it's not the same thing as the order of a reactant. And sometimes they do agree. It's just by mere coincidence, especially when you're dealing with elementary reactions. But when you're dealing with reactions that are very complex, that are made up of multi-steps, you need to determine experimentally the rate law by performing experiment to find the order with respect to each of the reactant. So I've said something about elementary reaction. If I tell you a reaction is elementary, I balance it for you. You can use the stoichiometric factor in place of the order. But if it is not an elementary process, then of course you must perform an experiment that will enable you to determine the rate law. Look at the quiz. Look at this very quickly before we go. A is reacting with 2B. What I'm saying, in front of A is 1. In front of B is 2. That 2 does not stand for the order with respect to B. The one in front of A does not stand for the order with respect to A. You need to determine what is in front, what the order with respect to A with order respect to B. A, the one stand for the order reaction is an elementary process. So how do you do this? Look at that. The rate of formation of D in their both reactions experimentally to be independent of the B. So the order is B rate equation, if you like. If you want to include B, you raise it to power 0. But what happened? The concentration of, is still dependent on the concentration of B and increases 4 times when the concentration of A is double. Write the rate law. It means the order respect to B, with respect to B is 0. With respect to A is 2. And then you can write the rate law of that particular reaction. And that is rate is equal to A. It is equal to K into A raised to power 2 and into B raised to power 2. So you can cancel, and that is rate. Oh, it's almost time. Rate is equal to K into A. You raise the A to power 2 and you raise the B to power 0. Anything raised to power 0 is 1. You can remove the B, or if you put the B there, you must raise it to power 0. So I have left you with what you should do now is answer this question. Look at that. Question 2, rate is equal to K into A. A is raised to power 1, B is raised to power 2. The overall order is 2 plus 1, okay? So what happens if the concentration of A is triple? If you increase A 3 times, what will happen to the rate of reaction? Will it be half? Will it be double? Will it be triple? Will it remain the same? Just try and answer them. It's part of the, look at that. How is the rate of disappearance, question 3, of hydrogen gas related to the rate of appearance of methanol? This is what I taught you yesterday. Write for the rate of decrease of carbon 2 oxide and hydrogen, rate of decrease of hydrogen, the rate of increase of the methanol, and find out how the rate of disappearance of hydrogen is related to the rate of appearance of and then this is the other one. What is the overall order for the reaction represented by the rate law? So that is the rate law, okay? Nitric oxide and hydrogen. The one is 2, the other one is 1. You add it together, and that will give you third. And so those are, they will take us, this will be topic for next week. And by Monday, I'll add more units. So go there and find out what you can do. Have a nice weekend.